Hi everybody, this is section 12.2, and in here we're going to look at different lengths of chords and properties of chords, and then arcs as well. Right, so a chord is a segment whose endpoints are on the circle. Chords could go through the center of the circle and form a diameter, but they don't have to. So as you can see here, we have chord PQ. It does not go through the center of the circle, so it is a chord in the circle. And then the related arc, or the intercepted arc, is also PQ. Right. The first theorem we're going to look at, and we're also going to do its converse as well, is the congruent central angle and arcs theorem. And this theorem says that within a circle, or in congruent circles, congruent central angles have congruent arcs. So if you have two angles that are the same in a circle or in congruent circles, their intercepted arcs will also be the same. That's what this theorem and the converse is saying. Next, we have the congruent central angles in chords, and this says that within a circle or in congruent circles, so again, if you have two that are exactly the same, congruent central angles have congruent chords. So in this case, right here, the central angles would be the same, but also the chord connecting the endpoints of that angle. So BA, chord BA, or chord CD would be congruent as well, because the angles are the same. Next, we have the congruent chords and arcs theorem. And this theorem says that within a circle or in congruent circles, congruent chords have congruent arcs. So again, if the chord is the same length, two chords are the same length within a circle, their intercepted arc would be the same measure. All right, we have two more theorems to look at here. And this one, the first one says the measure of an angle formed by two chords that intersect within a circle is 1/2 the sum of the measures of the arcs intercepted by the angle and its vertical angle. So think, if you have an angle that is formed on the inside of a circle by two chords that meet. So here's the center of the circle. Here's my first chord. Here's my other one. Okay, so they don't go through the center. But if I wanted to find the measure of either this angle here or this one because it's vertical, it's 1/2 the sum of the intercepted arcs. So now I'm going to take these two arcs, add them together, and then divide by 2 to find the measure of this angle right in here. So it would be, if I labeled it, we'll call that A, B, D, and we'll make that E right there. So the measure of angle AEB, or its vertical angle, is equal to 1/2 times the measure of arc AB plus the measure of arc CD. So inside angles add, outside angles subtract those arcs. And then we also have if two chords intersect within a circle. So here's my circle. Here's the center, and then we'll draw our two chords. So here's one, here's another. We just call them, we'll call it A, B, C, D. Make that E right there. All right, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So now we're talking about the lengths of the segments, and product means to multiply. So they're saying that segment AE times segment EC, so that will give us our first chord right here, is equal to the length of segment BE times segment DE. All right, so here, what we're going to do is we're going to look at the second theorem, just to kind of go through it. We talked about the formula on the other slide. Now we're going to do a problem to help us understand it. So here I'm going to draw us a larger circle. Here's my circle. There's my center. And then we'll put in our two chords. Again, they will not meet at the center of the circle. And we'll label our points, I'll call it A, B, C, D, and E. And then if I know that I have my lengths of my chords, we're going to fill in some measurements. So if I know that, trying to find my problem here. All right. AE, we'll make that E right there. Is going to be the measure 8. So this is angle AEB, right here, or its vertical angle. And then BE is 4. Is equal to. So here are the measurements of our chords. To find X, remember the product of the two sides are equal to the product of the two segments, other parts of the segment. So AE, if I did 8 times EC, so that whole chord, 8 times X minus 3, is going to be equal to 4 times X plus 5. Now we have to distribute, so I end up with 8X minus 24 is equal to 4X plus 20. I'll subtract 4X from both sides. So I get 4X minus 24 is equal to 20. We'll add 24 to both sides. So I get 4X is equal to 44. If we divide by 4, that means X will be 11 to find that length of that segment. All right, here we have two circles, and circle O is congruent to circle P. And so that means we are given that segment BC is congruent to segment DF. So because BC is congruent to DF and the two circles are congruent, that means that circle or angle O has to be congruent to angle P, because within congruent circles, congruent chords have congruent central angles. So BC and DF are my congruent chords. And then arc BC must be equal to arc DF as well, because if you have congruent circles, congruent chords have congruent arcs as well. All right, our next theorem and its converse is the chords equidistant from the center are congruent theorem. And this theorem says within a circle or in congruent circles, chords equidistant from the center or centers are congruent. So if we know that our chords are equidistant, so if I measure from the center to the chord on both sides, and I know that distance is the same, then those chords are going to be congruent. All right, so here I do know, because they told us, that OQ and this other segment here that they didn't give us a name for, right here, this segment, they are both 9. The length is 9. And I also know that PQ and QR are equidistant or equal segments. So because these two segments are the same right here, these two chords must be the same as well. And I don't know the whole length of PR, but I know that this is 12.5 and this is 12.5 because they're marked the same. So if I did 12.5 plus 12.5, we should end up with 25. And if this segment is 25, that means that SR is congruent to that. So SR or RS is equal to 25 units. All right, so our next theorem says if in a circle you have a diameter that is perpendicular to a chord, then it's going to bisect the chord and its arc. So here we have OA is perpendicular to CD, so it bisects the chord. So CE is congruent to ED, and then also arc CA is congruent to arc AD as well. Our next theorem says in a circle, if a diameter bisects a chord, that is also not diameter, then it is perpendicular to the chord. So it's really the converse of the theorem that we talked about before. So if we know we have a diameter that bisects a chord, we know that diameter is going to be perpendicular. So it's going to form a 90-degree angle. And our last theorem for this section is in a circle, the perpendicular bisector of a chord contains the center of the circle. So if you have a perpendicular bisector that runs through a chord, it's always going to be a diameter. It's always going to go through the center of that circle.